Quindi possiamo cominciare. Allora, come vi avevo anticipato ieri, continuiamo adesso sul modulo 2, che è questo modulo un po', diciamo, formale, teorico, che però ci dà tutti quanti gli strumenti e gli ingredienti che poi utilizzeremo per poi studiare effettivamente la fisica delle particelle. La lezione di oggi è particolarmente importante perché oggi, e anche continueremo la prossima volta, introdurremo appunto diciamo, il formalismo della meccanica quantistica e relativistica, come fu originariamente introdotto da Dirac nel 1928 e come poi ovviamente questo evolverà nelle teorie di campo, come vedremo anche la settimana prossima. Okay? Quindi diciamo il linguaggio e la notazione che introdurremo oggi ce la porteremo avanti per tutto il corso. Dunque, passo all'inglese. So, to correctly describe the dynamics of high-energy elementary particles, we need to adapt the concept of quantum mechanics to the principle of special relativity. We know that we can treat particle physics only in a relativistic regime in most of the cases. And so, in a sense, we need to make quantum mechanics invariant under Lorentz transformations. Okay? And in other words, this means that we must require that space and time are treated in the same way, the same footing. Okay? Now, let's start as an example from the Schrödinger equation. The Schrödinger equation, as you can immediately see, is not Lorentz invariant because the time and the spatial derivatives appear at different order. We have a first derivative in time, but second derivative in spatial coordinates. And therefore, it cannot describe relativistic particles. So we need to modify the Schrödinger equation to accommodate these with special relativity. In other words, we need to find a new equation that describes the dynamics of elementary particles in a Lorentz invariant way. And the first approach was proposed by Klein-Gordon. So let me now switch to the blackboard and let me show you how Klein-Gordon tried to merge quantum mechanics with special relativity. So I go here now. Mi è chiaro come... No, qui si vede sempre la slide. Come faccio a passare alla lavagna? Ieri riuscivo a farlo in modo automatico, adesso non sto riuscendo. Un momento, ragazzi. Compagliara, siete riusciti a vedere la lavagna? A fare la parte della lavagna?
Sì, sì.
Sì, sì.
Perché non va, cosa che devo abilitare? Non mi è chiarissima questa cosa. Se vado da qui, no, qui sto registrando. Oh, che faccio? Interrompo la presentazione? Provo un po' così. Così vedo Leo. Così non vedo più niente.
Dovrebbe poter accendere la videocamera sotto.
Ah, c'hai ragione, è sconnessa, pensavo l'avessi lasciato accesa. Ok, allora torniamo alla presentazione un secondo. Sì, vabbè, quello è il problema. Ok. Allora, innanzitutto torniamo alle slide e poi attivo la telecamera. Ecco qual è il problema. Allora, adesso dovreste rivedere le slide di nuovo, giusto?
Esatto.
Ora attivo la telecamera e adesso se io vado qui. Ok, adesso vedete me la lavagna, giusto?
Corretto.
Perfetto. Giusto. Ottimo. Allora, ancora un po' di dimestichezza con questo sistema. Allora, so we were saying that the first approach to merge non-relativistic quantum mechanics with special relativity was attempted by Klein and Gordon. So, the idea of Klein and Gordon is the following. Instead of using the standard wave function, okay, the time-dependent wave function, they rather introduced, let's say, a Lorentz invariant wave function. That is a wave function expressed in this way: x0, x1, x2, x3. Or, as we studied in the first lesson, for the position for vector, this is just psi of time minus x minus y minus z. And we can also write in a compact form in terms of the Lorentz index. Okay. So the starting point was the substitute the standard non-relativistic, so non-Lorentz invariant function with every function which is now a function of the for vector position for vector. So which is now, of course, Lorentz invariant. Now we can introduce the momentum operator, mu, as much like the same way we do in non-relativistic quantum mechanics, but now, of course, using the Lorentz index. X mu is equal to 0, 1, 2, and 3. Okay? So in quantum mechanics, we just have the spatial, derivatives. Here you also have the time component. In particular, for the time component, that is the 0 component, the 0, is I, h bar, and that is the x0. But x0 is in time, so this is I, h bar, d over the c time, and we can also write as I h bar 1 over c that over negative. And so it turns out that if you now multiply by c, you obtain for the 0 component d0c equal to I h bar direct negative. But as you know, it is nothing else than the energy operator. Okay? So we define here the energy operator, which is given by I h bar and then the time derivative. What about the other three components? Then we have the spatial terms. Okay, d is equal to minus I h bar, and then we have the special derivative that we can write in a compact way to the nabla operator. So the nabla operator, as you know, is a differential operator defined this way. That is the x1 plus that in the x2 plus that in the x3, x3. Okay. So we have now, let's say, translated in a Lorentz invariant way the momentum operator, which we can split in a zero component, which is the energy, and in the special component, which is the standard momentum. Now, let's start again. This is still the idea from let's start again from the relativistic relation between energy, momentum, and mass. So as we know, E is equal to square root of P squared C squared plus M squared C to the fourth. Okay. Now we take the square of this, so we're gonna have E squared is equal to P squared C squared plus M squared C to the fourth. We divide by 1 over C squared. So we have 1 over C squared. P squared is equal to P squared plus M squared C squared. Okay. So now, okay, we have a Lorentz invariant relation between energy, momentum, and mass, and we can now substitute here the corresponding energy and momentum operator here and there, and apply those operators to the Lorentz invariant wave function. Okay, so this is the main idea of time Gordon. So from here, this we can transform as 1 over c squared E squared operator over the Lorentz invariant wave function. This is equal to p squared operator over the Lorentz invariant function. And then we have plus m squared, c squared, and again the Lorentz invariant wave function. And now we substitute the expression of these operators into our equation, okay? So, taking a proper account of the signs, this is minus 1 over c squared, h bar squared, d in the t, so the second derivative of the wave function, is equal to minus h bar squared, nabla squared, over acting on the wave function, plus m squared, c squared, psi x move. Okay, and now since we are now working in a relativistic, so in a Lorentz invariant framework, we can put together the time derivative and the special derivative, which both now appear at the second order. So we can collect them at once. So this is 1 over c squared d over dt minus nabla squared. So this is our full differential operator, okay, acting on the Lorentz invariant wave function, plus m squared c squared over h bar squared psi x move equals 0. And this is the famous Klein-Gordon equation. Okay, so let me just summarize. So we started from translating the standard non-relativistic wave function into a Lorentz invariant wave function in terms of the position for vector. So we redefine now the energy momentum operator, okay? But now these are the zero and the special component of a four-dimensional operator. Then we start from the relativistic interaction between energy, momentum, and mass, take the square, and we substitute these operators into this equation. We collect the differential operators at once, and then we obtain these the Klein-Gordon equation. Okay. Okay. So let me now give you some more details about this equation. We switch now back to the slides. Ok, vedete la slide?
Sì.
Ok.
Sì.
Ok.
Sì.
Okay, so this is the equation we derived, the Klein-Gordon equation, and now this is clearly Lorentz invariant because both the time derivative and the special derivative are both at the same order, so are both second order, whereas in the Schrödinger equation, only the spatial derivative are second order and the time derivative was only third order. Okay, so this is now, let's say, manifestly Lorentz invariant. We can also write this in a more compact way, in the so-called covariant form. Okay. So this is also a notation that we will be using. Okay, we can again merge now the time derivative and the special derivative into a derivative over the four vector x move. Okay, so this whole parenthesis here reduced to this term here. Then we can also collect the mass term inside the parentheses. Okay, and this we can even write in a more even more compact formalism. Okay, so all these second derivative just one can write like the mu in the mu. Okay. Then in natural units, of course, we forget about the C and H bar. And so this is, at the end, the Klein-Gordon equation in the manifestly covariant form, okay? But now we have the Lorentz index, of course, running from 0 to 3. Now, a few details about this equation. First of all, what can we do with this equation? The Klein-Gordon equation describes the dynamics of free particles, so there is no interaction potential here, as you can see, at this level. With mass m, the m of the particle enters here in this term, or here, and spin 0. So this is important. So this equation here only works for, let's say, relativistic scalar bosons. Okay, it does not work for fermions, such as leptons and quarks. And this is one of the main limitations of this approach. But there are also other problems. Okay. First of all, we started from this equation here, okay, which comes with the energy to the square, and so as a consequence, we have to expect both positive energy solution, but also negative energy solution, okay? Here, when we take the square root, we have a plus or minus here. And at the moment, we don't know how to interpret the negative energy solution, okay, which are, in principle, one can say they are unphysical, okay? This we will see later on how to do. There is another problem. Also, the Glenn-Gordon equation leads to negative probability densities, which of course makes no sense, okay? Probability density must be, of course, positively defined. And this is a consequence of the second derivative versus time. Okay, so having a second derivative versus time is a problem. We have to solve this problem. But then if we want to treat time and space on the same footing, that means that we have also to change the order of the spatial derivative. And then there is another problem. That is, when you now apply the Glenn-Gordon equation to the case of a particle into an electromagnetic potential, so not anymore for a free particle, but a particle interacting in an electromagnetic potential, and then you make your calculation, you obtain a value of the fine structure constant, which is completely different than the correct value, the one you can obtain from experiments, for instance. Okay. So the Glenn-Gordon equation, let's say, works pretty well in describing the dynamics of relativistic scalar bosons, but then it fails in many important respects. Sorry. Okay, so let's see now how some of or all of these problems have been solved. The solution came by Dirac. Okay, so Dirac in 1928 derived a new quantum relativistic equation of motion. Okay, which is still, of course, a Lorentz invariant. And now the difference is that both the time derivative and the spatial derivative come at the first order. So they are at the same order, of course, because you want to have a Lorentz invariant structure, but they come at the first order, whereas in the Glenn-Gordon they were both at the second order. So this is essentially the basis of the Dirac equation. Okay, you can also write it as in terms of the eigenfunction, eigenvalue equation in this way, where HD is the Dirac Hamiltonian that we can write in this way. So it essentially is has a linear dependence on the momentum operator. That means a linear dependence on the nabla, so on the spatial derivatives. Okay, and we have here essentially three parameters: a scalar parameter beta and a vector parameter, which comes with three components: alpha 1, alpha 2, alpha 3. Okay. But the most important thing to notice here is that both the time derivative and the spatial derivative enter at the first order. Now, let's see more about these parameters, okay, or whatever they are. So this is a vector, so it comes with three components, and this is a scalar. And now, in order to make, in order that everything here makes sense, these objects, so A1, A2, A3, and beta, have to be 4 by 4 matrices. So not just numbers, but 4 by 4 matrices. And these matrices have to be chosen in such a way to fulfill the relativistic relation between energy, momentum, and mass. And this is only possible, okay, one can show it is only possible if the square of each of these matrices is the identity matrix, the 4 by 4 identity matrix, and also if they follow these anti-commutation relations, okay, ij alpha I, alpha j plus equal to minus alpha j alpha I, essentially, and a similar relation for alpha and beta. Now, what kind of matrices we can use here? Okay, of course, there are several possibilities, but the common choice is to write down the beta matrices in this way, where I is a 2 by 2 identity matrix. So overall, this is a 4 by 4 matrix. Okay, and the three alpha I matrices are given by are expressed in terms of the three Pauli matrices. Okay. So this is sigma 1, sigma 2, sigma 3. Again, this is a 4 by 4 because each of those is a 2 by 2 matrix. So this is essentially the common choice, but obviously this is not the only possible. You can also make a different choice, and things would still make sense. So now, okay, when we now write explicitly the Dirac Hamiltonian, okay, we obtain the Dirac equation in this explicit form. Okay, where again, let me remind once more that the time derivative and the spatial derivative come at first order. There is another way to express the Dirac equation, and this is through the so-called Dirac matrices, gamma mu, where mu again is the Lorentz index that runs from 0 to 3. Okay, and these Lorentz method, these Dirac methods have to fulfill again some constraints, okay, which derive from these constraints here essentially. Okay, and in particular, it turns out that the gamma zero, so the first component here, is equal to the beta matrix that we defined before, and the gamma I are given by this matrix product beta times alpha I, where I, of course, runs from 1 to 3. And once you use this definition, okay, this is the explicit form of the four Dirac matrices. Okay, gamma 0, gamma 1, gamma 2, and gamma 3. And of course, they have to fulfill these kind of properties in order to be to cope, okay, with the requirement that this equation is satisfied here. Okay, so the requirement here are that the square of gamma 0, okay, is the identity matrix. The square of any of the gamma I is the minus identity matrix, and then they have to anti-commute in this way. Okay, so let's now make use of this formalism to derive the Dirac equation in the covariant form. Okay, so I will switch to the blackboard. Finisciamo. Okay. Okay, so we start from the Dirac equation in the explicit form that I will provide you. So I, h bar, the peak psi, plus I, h bar, alpha, scalar, lambda, psi, minus beta, m psi is equal to 0. Okay, so this is our starting point. Now we multiply the Dirac equation on the left by beta. So this is I, h bar, beta, the peak psi, plus I, h bar, beta, alpha, scalar, lambda, minus beta squared and psi equal to 0. And now finally we translate the beta and alpha matrices in terms of the Dirac matrices, so the gamma matrix. So this turns out to be I, h bar, the beta is nothing else than the gamma 0, okay? And then we have the time derivative of psi plus I, h bar, beta alpha is the gamma matrices, scalar nabla, psi, minus, and beta squared is equal to the identity matrix, so this is plus minus and psi equal to 0. Okay. So this is now an equivalent way to write the Dirac equation. Okay. Now in terms of the Dirac matrices, Dirac gamma matrices. This we can make even more compact, as we've done for the Gleigold equation. So let me remind you that we can first merge the time derivative and the spatial derivative. So this differential operator we can write as z in the x0, z in the xk. Minus sign here, and thus you can write in a very compact way as z in the x mu or even the mu. Okay, so this is the first derivative over time and the three spatial coordinates. And so once you do so, you can now rewrite your Dirac equation in a compact and explicitly covariant form. It is I, gamma mu, the mu minus m psi equal to 0. Of course, we are working in a natural unit, so we have to h bar equal to 1. Domanda, queste cose qui le avete già viste in altri corsi? Plain Gordon e equazioni di Dirac?
No, mai.
Ah, ok. Le vedrete per chi di voi farà sicuramente quantum field theory. Ok, quindi sono io il primo a spiegarvi, va benissimo. Vabbè. Torniamo adesso alle slide. Okay, and this one is now, okay, the Dirac equation in the fully covariant form, the one that we derived on the blackboard. Now, let's now discuss a bit about solution of the Dirac equation, okay? So, or the shape of the wave function that satisfies the Dirac equation. So, we are dealing now with 4x4 matrices. So, the wave function, the eigenfunction psi of the Dirac Hamiltonian cannot be a normal wave function, but it has to be a 4-component vector this way, which we will call spinor or spinor. And the reason, as you see, it is related with spin, and this will be clear on the next lesson, okay, on next Wednesday. So the solution of the Schrödinger equation must be a 4-component wave function or spinor. Let me make here just a note, just for your knowledge. If Dirac fermions were massless, so suppose that quarks and leptons were massless, then we would of course need to modify the Dirac equation, and in particular we do not need the mass term, which is the beta term. Okay. Okay. If your fermions are massless, you don't need this term here. And so at the end, the Dirac equation is a very extreme case. Okay, you can only text just in terms of the alpha matrix, or even more simply, you would just need 2x2 Pauli matrices. Okay, so this kind of equation is called the Weyl equation, and the solution are called the Weyl spinor. And so in this case, they are not anymore 4-component spinor, but only 2-component spinors. Okay, and this formalism was adopted for the case of neutrinos. You know, the neutrinos until, let's say, the end of the 20th century were supposed to be massless. So we're supposed to be solution of the Weyl equation. Now, of course, we know through the discovery of the neutrino oscillation phenomenon that we will be studying, of course, in our course, that neutrino must have a mass, a very small mass, but still a mass. Okay, so this is not anymore true. Okay, this was a detail. Now, let's continue on the formalism. Let me now introduce, so we define the spinor, or spinor. Let's introduce now the adjoint spinor. The adjoint spinor is indicated by this in this way, so with a bar on the top, and it is given by the Hermitian conjugate of your spinor times the gamma zero matrix. So when you do this, okay, you can make this explicit. Okay, so the Hermitian conjugate is the transpose of the complex conjugate, and then you multiply by gamma zero. So this is now your adjoint, your Hermitian conjugate spinor. You multiply by gamma zero, and you obtain the full expression of the adjoint spinor. Let's now derive by using the concept of adjoint spinor, the so-called adjoint Dirac equation, which is also very relevant, as we will see. So let me turn back to the blackboard. All right. Okay, so we start again from the Dirac equation in the explicit form. So it's I, gamma zero, then the t psi, plus I gamma k, then the xk, k psi, minus m psi equal to 0. Okay, now I just made explicit the number operator in terms of the first order derivative, and of course the index k runs from 1 to 3. And the 0 term is put apart in this equation. Okay. Now let's take the Hermitian conjugate of these equations. And we indicate with this symbol here, which is called the dagger. Okay. So let's take the Hermitian conjugate of the derived equation. And in doing so, I need I take the side of the blackboard to write down the main ingredients. Okay. So the Hermitian conjugate, as we know, of the spinor is the transpose of the complex conjugate. Then we have gamma mu that in the x mu psi Hermitian conjugate. When we take the Hermitian conjugate of this term here, which is this one, this turns out to be that in the x mu. Then we have the Hermitian conjugate of the spinor and then gamma mu at the end. And the order here is important, okay? The order is important. It's not and then finally, the other thing that we need is the Hermitian conjugate of the gamma matrix, gamma k. This is minus gamma k, with k equal to 1, 2, and 3. And so, for instance, for the zero component is the only one that contains the sign. Okay, so these are our transformations that we have to put into the Hermitian conjugate derived equation. So let's now substitute all these in our equation. So we're going to have minus I, the minus is close to the technical complex conjugate here, that in the T, and we have the Hermitian conjugate spinor, gamma 0, minus I, that is the xk, and then we have the Hermitian conjugate spinor, times minus gamma k, okay, it comes from here, and then we have minus mc daga is equal to 0. And this we can write in a more in a better way, okay? Of course, we change also sign here, so this we can also write in an equivalent way as that in the psi gamma dt gamma 0 minus I, that psi gamma daga in the xk gamma k plus m psi daga equal to 0. Now, this equation is still not completely Lorentz invariant because the time derivative, the special derivative, comes with a different sign. It is a plus sign, it is a minus sign. So we have to make another change here. Okay, we don't need anymore. And we have to exploit essentially this property of the gamma matrices. Minus gamma k gamma 0 is equal to gamma 0 gamma k. Okay, the anti-commutation relation. So this actually becomes, so we multiply on the right by gamma 0, this equation here. So we're going to have I, the psi daga with t, gamma 0, gamma 0. So we are multiplying by gamma 0 on the right, sorry, this one, okay, plus I, the psi daga in the x, k, gamma 0, sorry, this is the minus gamma k gamma 0 plus m psi daga gamma 0 equal to 0.
Professore, scusi,
Sì.
ogni tanto capita che scrivere e non si vede bene la lavagna.
Ogni tanto non si vede bene?
Per esempio, quest'ultima equazione non si leggono tutti gli indici, gli apici, ecco.
È una questione di risoluzione o di calligrafia mia?
Ditemi anche voi, altri ragazzi, se...
Posso scrivere un attimo più in basso la prima riga più in alto?
Come dici, scusa?
Scrivere un po' più in basso la riga che ha scritto adesso.
Ok, questo deve stare un po' più giù, va bene.
Scusi.
Provo a scrivere un po' più grande, magari. Ok. So I, the psi daga in the t, gamma 0, minus I, the psi daga in the xk, gamma k, gamma 0, plus m psi daga gamma 0 equal 0. Riuscite a vederla questa?
Sì, sì, molto meglio.
Okay. Now we apply this property here. Okay. So we switch the two, we swap the two, and we also change sign here. So at the end we're going to have psi gamma daga in the t. This object here, okay, this we can actually retain. So we put here gamma 0 and then gamma 0. Let's collect it this way. Plus I, the psi daga in the xk. Now we swap and change sign, so this is now gamma 0, gamma k, plus m psi daga, gamma 0 equal to 0. Okay? And now we are done, because we just have to remember how we define the adjoint spinor. So the adjoint spinor is exactly this one, okay? This is the emission conjugate times gamma 0. And so this we can at the end write as I, the of the adjoint spinor in the t, gamma 0, plus I, the xk, adjoint spinor gamma k, plus m adjoint spinor equal to 0. And the question we just derived is the adjoint Dirac equation. And it is now manifestly Lorentz combined, because the time derivative and the special derivative come with the same sign, thanks to this substitution. The importance of the adjoint Dirac equation will become clear in the next lessons. Okay? Now, we are back here. So let me also put in your slide the adjoint equation that we just derived, okay? And this again, once more, can be written in a more compact and explicitly covariant form, okay, by using the compact differential operator. Be careful now that if you write this in this way, the derivative act in the adjoint equation, the derivative act to the left. So the wave function or the spinor has to stay in the left side, not in the right side of the equation, okay? Okay, so now we have derived the Klein-Gordon equation and the Dirac equation and the adjoint Dirac equation. Let's see if now the adjoint, the Dirac equation can solve at least two of the problems raised by the Klein-Gordon equation. Okay. First of all, let me derive this continuity equation. So by multiplying the Dirac equation on the left by the adjoint spinor, and the adjoint Dirac equation on the right by the spinor, and summing up the two resulting equations, one obtains the continuity equation, which is the analogous that you obtain in non-relativistic quantum mechanics, okay? Where rho is the probability density and J is the probability current. So let me derive this once more on the blackboard. All right. So we start from the ordinary Dirac equation. So our starting point is always the same. So it's I gamma 0, the in the t side, plus I gamma k, the xk side, minus m side equal to 0. Okay? And now we multiply this equation on the left by the adjoint spinor. So we're going to have I adjoint spinor, gamma 0, the unity psi, plus I, adjoint spinor, gamma mu, gamma k, sorry, the xk psi, minus adjoint spinor, mass, so the mass will put to the free, spinor equal to 0. Okay, so we took the standard direct equation, we multiply on the left by the adjoint spinor. Now we do the same exercise, multiplying on the left the adjoint equation by the normal spinor. So we're going to have another equation, I dt psi bar gamma mu psi plus I del in the xk psi bar gamma k psi plus psi bar and psi equal to 0. Okay, so this is the adjoint direct equation now multiplied on the right by the standard spinor. And now we sum the two. Member to member. So we have I psi gamma 0 that in the t psi plus this term here plus that in the t adjoint spinor gamma 0 psi plus now we add the second terms I c bar gamma k that in the xk psi plus this one here plus that in the xk adjoint spinor gamma k standard spinor. And then these two just cancel. They are the same and they come with opposite sign. So this is just equal to 0. Let's now look into these parentheses here. And you realize that these are both the derivative of a product. You see, this is the first not derivative, not lo dico in italiano, faccio prima, dai. Primo pezzo non derivato per derivare dal secondo, più derivato del primo per la seconda non derivata. Anche qui, primo non derivato per derivata della seconda, più derivata della prima per la seconda non derivata. So this is the definition of the derivative of a product. And so this we can write here in the compact form as the t of psi bar gamma 0 psi plus the xk of psi bar gamma k psi equal to 0. Okay, you can check yourself by doing the derivatives. Now, this is the probability density. Let's call it rho. Probability density. Okay, and the second term, okay, with the k matrix, so with the spatial component, this is the current, the vector, and this is the probability current. So now we can merge the two in a Lorentz invariant way. So we merge the time derivative and the special derivative. So this is equivalent of the xk of adjoint spinor gamma mu spinor. Okay, that we can also write in an even more compact way. So this is an arrow. Okay, as j mu, and this is equal to 0. And now this j mu, which is defined in this way, where now mu goes from 0 to 3, j mu is the 4 current or 4 probability current. Okay, it's a 4 vector. If we can also write more explicitly in this way. So the 4 currents, j mu, we can write as a 4 vector at the time the 0 component, which is the probability density, and then the probability current, which is a vector, this vector here. Okay, this is gamma mu psi equal to 0, 1, 2, and 3. Okay, so our main result is that the derivative of the 4 current is 0, and this means that the 4 current is conserved. So if you now go back to the slide, you will see that we just derived the continuity equation that you know from non-relativistic quantum mechanics. Okay, this is exactly what we derived. This is the zero component and this is the special component. Altogether, this is the for current and its derivative is zero. Okay, this is summarized now here. Okay, so the for current is zero, and so the for current is a 4 vector defined in this way in terms of the adjoint spinor and the direct matrix is a conserved quantity. Let's consider as an example the zero component, so the probability density rho zero, which is the zero component of the for current. Okay, this is of course psi bar. Sorry, you don't see it. Sorry here. Psi bar gamma zero psi. Okay. Now you use the definition of the adjoint spinor as the Hermitian conjugate times gamma zero, and then you remember that gamma zero squared is the identity matrix. So this is just psi daga psi, or if you want, this is just your probability density. And so the way it is defined is always positive. Okay, you end up with this quantity, which by definition is a square, so it is always positive. And this solves one of the problem of the Klein-Gordon equation. Okay, that we just mentioned, but we didn't derive, but you can also derive it as an exercise. If you calculate now the probability density from the Klein-Gordon equation, you end up with a relation of this type, where you have a minus sign here. That means that it can be positive if this term is more than this one, but it can also be negative if this term is greater than this one. Okay, and of course, a negative probability density is something that makes no sense. Okay, so the Dirac equation was able, for the moment, at least to solve the problem. Okay, so it results in a probability density which is positively defined. Now, we can also multiply our current by a coupling constant. If you use the electron charge, for instance, this 4 vector will correspond to the electron current density. Okay, and this we will, of course, use when we will deal with the quantum electrodynamics. Okay, so this object transforms as a 4 vector, and it has the physical meaning of the electron current density. Now, how many possible ways we have to construct a current? Okay. If you want this current to be Lorentz invariant, there are only 5 ways that you can construct a current, okay? And each of these terms, as you see, is of the form psi bar. Then there is some combination of 4 by 4 matrices, and then there is psi. So it's the adjoint spinor and the spinor, okay? So the only possible Lorentz invariant current that you can create are those ones. The scalar current, which is simply psi bar psi. The vector current, which is exactly the one we derived now, okay? And this transformed as a scalar, this transformed as a 4 vector in Lorentz, with Lorentz transformation. Then there is also a tensor current, okay, where we now this tensor sigma nu is given by this combination of gamma matrices. Then we have the axial vector current, okay, with this combination of gamma mu, gamma 5, where gamma 5 is defined in this way. Okay, gamma 5 is this combination of the 4 Dirac matrices. And finally, we have the pseudoscalar current. Okay, so take these in memory, because we will, of course, make a lot of use of this current. Actually, all of them except the tensor. Okay, all these 4 we will make a heavy use during our course. Okay. Ok, facciamo una pausa?
Va bene?
Ok, dopodiché riprendiamo alle 12, poi continuiamo appunto a spiegare un pochettino, descrivere le soluzioni delle equazioni di Dirac. Ok?
Va
Ok,
bene.
ripartiamo alle 12. Ok, ragazzi, ci siete?
Sì, sì.
Ok.
Ok, bene. Allora, riprendiamo da qui. Okay, so we have introduced the direct equation and the adjoint direct equation, and we've seen how when we merge them, we obtain the standard continuity equation, but now of course, in the Lorentz invariant way. And we have just seen all the possible ways to define a Lorentz invariant current in relativistic quantum mechanics. Okay, so we will of course come back to this in the future. Now, back to the direct equation. We have said a lot about the equation. We have not discussed about the solution of the equation. Okay, so the shape, the analytic form of the solution of the direct equation. So let's consider first the simple case of a free particle, so not interacting particle. And so the solution, of course, must be in the form of a plane wave. So our spinor is in this way, okay? This standard notation, but now the useful notation is this one, okay? So we can split our spinor into a plane wave and this U, which is in fact the 4-component spinor, okay? Which can further be split into two-component spinor. The phi spinor, which is a 2-component, which is the upper component, and the chi spinor, which is again a 2-component, which is the lower component. So overall, we have always, of course, 4 components. And to extract the functional form of the Dirac spinors, so the solution of the Dirac equation, it is convenient to solve the Dirac equation in the form of eigenvalue equation. So this is the Dirac Hamiltonian. This is our eigenfunction in this guy here. Okay, this is the eigenvalue. And then we can make explicit, of course, the Dirac equation in terms of this linear dependence on the momentum operator, so the derivative on the special coordinates and the mass term. So let's switch again to the blackboard. All right. Okay. So we start with our Dirac Hamiltonian acting on the new eigenfunction. It is alpha p plus beta m q, and then this is equal to e u. This is our eigenvalue equation. Let's now make explicit the alpha matrices here. So this is equivalent to 0, sigma, sigma 0, which are the Pauli matrices, if you remember, scalar p plus, let's make explicit also the beta matrix, I, 0, 0, minus I, m. And then we split our 4-component spinor into the upper component and the lower component, and this is equal to E phi chi. Now we add these 2 matrices here, okay? So this term is 0 plus Im, so this is mi. This term now is sigma p plus 0, scalar p. And then similar, we have sigma scalar p here and minus m I here on phi k equal to E phi k. So we just add these 2 matrices here, element by element. Now this we can write also in equivalent form as a system of equation. So we have m I phi plus sigma scalar p chi equal to E phi and sigma scalar p phi minus m I chi equal to E chi. Okay. Just take the problem with this, okay? M times p plus sigma p times p, and then the other one. We equate into the upper and the lower component. And now we can also rewrite this system in a more convenient way. has E minus M I chi minus sigma scalar P chi equal to 0 and minus sigma scalar P phi plus E plus M identity matrix chi equal to 0. Now, if you look at this system, you realize that there are no constant term, okay? So this is a suppose homogeneous system of equation. And in addition, each of these two equations has two components. So overall, this corresponds to a system of 4 equations. And so we expect to have 4 solutions. Now, let's solve this system. And as you know, the system provides a non-trivial solution if the following determinant is null. So we take the determinant of this part here. So E minus Mi minus sigma scalar P minus sigma scalar P E plus Mi. Okay, so we want this determinant to be 0 in order for this system to have non-trivial solutions. So let's calculate this determinant. So we are going to have E minus M times E plus M I squared. And then we have the other diagonal, which is minus sigma scalar P, sigma scalar P equal to 0. Right?
Okay.
That's fine. So this is nothing else than P squared minus M squared, and this one can show that it is just P squared. Okay. The proof of this requires some algebra. I will not waste time on this. Just trust me, or try to derive yourself if you want as an exercise. So overall, what we take here is the standard arithmetic equation P squared is equal to P squared plus C squared, M squared. Which is, of course, always satisfied. Okay? This means that our system of equations always provide non-trivial solutions. Ok, vi lascio copiare quando avete do qualche secondo ancora per copiare.
Porco tu giuda.
Potete ragazzi chiudere i vostri microfoni? Tranne per fare domande ovviamente. C'è qualcuno che deve ancora copiare? Ok, no? Quindi torniamo sulla slide. So we have seen that the system provides a non-trivial solution if this relativistic relation is satisfied, which is always satisfied. Okay. But now again we have a problem because from this equation we obtain 2 solutions here. Okay, a positive energy solution and also a negative energy solution. So we have again the same problem that we had already from the Klein-Gordon equation. Okay, so also the Dirac equation provides solution with negative energy, and so we have to understand and interpret correctly this negative energy solution, as we will do later on. Now, so let's group now the solution in this way. So we have two solutions corresponding to positive energy. Okay, so these are the two positive energy solutions, and these are the two negative energy solutions. Okay, those two here. Now, let me also remind you that the system that we have seen before was an homogeneous system, so without constant terms. And it turns out that, this is written here, it turns out that in virtue of the homogeneity of the system, the two component spinors chi and phi are completely correlated, okay? So each solution contains both. You obtain these if you fix this one, you obtain this one if you fix the other one, and so on, okay? And additionally, all four solutions are needed to form a complete set of orthogonal vectors. So we cannot discard the negative energy solution. So this is, let's say, a brute beast that we have to deal with and also to understand. We cannot just discard these apparently unphysical negative energy solutions. Okay. Now, as I was saying, okay, the two solutions are strongly correlated because the system is homogeneous. Okay, that means that you can obtain one by making an arbitrary choice of the other, and so we will use the following. Okay, of course you can also make a different choice, but we will use the following choice. So for the positive energy solution, we will obtain the chi solution by putting an arbitrary hypothesis for the phi solution, and for the negative energy, we will obtain our phi solution by putting an arbitrary choice of the chi solution. Again, you could also make a different choice. This is the choice which is commonly made. Okay, so let's also now group here all the four solutions. So we have again two solutions with positive energy, two solutions with negative energy, and we call them U1 and U2 for positive energy, and U3 and U4 for negative energy. Each of these U is a four-component spinor given by two component spinors, phi and chi. Here the n are just normalization constants that we will define later on. And now we made explicit the solution that we found in the previous slide. Okay. So here, suppose we make an arbitrary choice of the upper component, and we will obtain correspondingly a lower component. This is the same now for the phi 2, and now the same here for the chi 1 and the chi 2. Okay. So what kind of hypothesis do we make for the arbitrary choices? Okay, so let's start with the positive energy solutions. Okay, the simplest orthogonal choices for the phi 1 and phi 2 are the following. Okay, it's just an orthogonal set of vectors 1, 0, 0, 1, like if you want to spin up, spin down. Okay, so let's now use this convention here and try to work out the full analytic expression of the positive energy solutions. Again, we switch to the blackboard. Okay, so our arbitrary choice is phi 1 equal to 1, 0, and phi 2 equal to 0, 1. Okay? E now, c'è la domanda?
Potrebbe scrivere più in basso, è ancora superato il
Sì,
limite.
questo sì perché non c'era niente di importante, la cosa che entrava in zero slide. Allora, P1 equal to 1, 0. Ok, mettiamo che qua ho un margine in alto. E mettiamo ancora la lavagna. And P2 is equal to 0, 1. Si vede?
Sì, sì.
Okay,
Sì.
so this is our choice for this set of solution. Let's now derive the full solution. So U1 is the first four-component solution with positive energy. It is given by M1, phi 1, chi 1. That is M1, and then we have phi 1 and sigma star P divided by P plus N I1. This is what we find in the slide. Okay. Let's now substitute this solution here. So this is going to be N1 times. Now we also make explicit the fact that these are two components. Okay, so this is 1, 0, and then we have 1 over P plus M. We make explicit also the scalar product, sigma P. So this is sigma 1 Px plus sigma 2 Py plus sigma 3 Pz that acts on 1, 0. Let's now make explicit the three Pauli matrices. Okay, so this is N1 that multiplies. So we have still 1, 0, and now 1 over P plus M that multiplies 0, Px, Px, 0, plus 0 minus I, Py, I, Py, 0, plus Pz, 0, 0, minus Pz, acting on 1, 0, that's it. Okay, so we just made explicit the form of the Pauli matrices and multiplied with the Px, Py, Pz, the non-zero elements. Now, as before, we have to add these matrices member by member, element by element. So it is N1, we have 1, 0, and now here we have 1 over E plus M. Okay, so here we have 0 plus 0 plus Pz. So it's just Pz. The other element is Px minus Ipy plus 0. So this is Px minus Ipy. Here we have Px plus Ipy plus 0. And then here we have 0 plus 0 minus Pz. All these acting on 1, 0. Let's put it here. This is N1 times 1, 0. Now we have Pz plus 0. And then we have Px plus Ipy times 0 plus 0. So this becomes a vector in this way, 1 over P plus M, and then we just have Pz here, and Px plus Ipy there, acting on 1, 0. No, this is already, this is done already, sorry. I have already multiplied by 1, 0, so this will not have anymore. That's it. And so we are done. Our solution then is U1 equal to N1. And so we have 1, 0. Here we have Pz divided by E plus M. And then we have Px plus I Py divided by E plus M. Okay? And it is our spinor psi 1, psi 2, psi 3, psi 4. Ok? Chiaro come siamo giunti qui?
Per me sì.
Ok. Quindi questa è la prima soluzione a energia positiva dell'equazione di Dirac. Ovviamente possiamo fare la seconda, ripetere lo stesso esercizio per la seconda soluzione a energia positiva. Non starò a ripetere i passaggi, vedo direttamente il risultato finale. So for the second positive energy, so U2, we're going to have N2, phi 2, chi 2, it is N2, phi 2, sigma scalar P divided by E plus M phi 2. This is the one you find in the slide, okay? And now by doing the same procedure as before, okay, this I will not do, we can do for exercise. We obtain N2 and then our co-component speed, which is now 0, 1. Let me remind you that the phi 2, the arbitrary choice for the second component was 0, 1. Okay? So 0, 1, and then we have pi x minus I dy divided by E plus M and minus Ez divided by E plus M. And this is the full expression of the second solution with positive energy. Okay? Siete tutti? Avete copiato tutti?
Sì.
Ok. Torniamo qui. Okay, so I put also in the slide these two solutions for completeness, okay, where now I also put explicit the normalization constant, which turns out to be square root of E plus M, okay? So this is now the full expression of the first two, the two solutions with positive energy. Now, of course, we can now work out the negative energy solution, which we cannot neglect. They are part of the set of orthogonal solutions. And now again, we make an arbitrary choice now for the chi1 and the chi2, which is always 1, 0, 0, 1. We do exactly the same algebra we did on the blackboard, and we obtain now the U3 and U4 in the same way. Of course, now they look different because these are the negative energy, right? And again, the normalization constant is still the same. So now we derived formally the four solution of the Dirac equation, two corresponding to positive energy and two with negative energy. Now the question is, how can we interpret the negative energy solutions? Okay. So when Dirac proposed his theory, which was very elegant from the mathematical point of view, etc., and it also described well the dynamics of electrons. It was described well the fine structure constant. It comes with the positive defined probability density and so on. But then the fact that it also allows for negative energy solution was a real problem for the theoretical community at the time. So the physicists were really skeptical that this theory could work because it allows for negative energy solutions which are unphysical. But Dirac was really convinced of his theory, and so he provided a mechanism to explain this negative energy solution, okay? And this is the mechanism of the so-called Dirac sea, okay? You have probably seen this already, I don't know, but let me just simply explain the idea of Dirac to interpret the negative energy solutions, okay? So Dirac introduced a new concept of vacuum. The vacuum is a state in which all infinite negative energy levels are occupied by electrons in accordance with the Pauli exclusion principle. So you can only have two electrons in each level with opposite spin. You cannot put more electrons in each energy level, okay? And the energy levels are all energetically the same energetic jump given by the mass of the electron squared, essentially. Okay. The mass of NC squared, the mass of the electron. Now, so the vacuum is like this. All the positive energy levels are empty. All the negative energy levels are occupied by electrons up to minus infinity, okay? According to the Pauli exclusion principle. So 2 electrons per each energy level. Now, of course, Pauli principle prevents positive energy particles that might be here to collapse into the negative energy levels, because these are completely filled, so they cannot accept more particles. Otherwise, it would violate the Pauli exclusion principle. Okay. However, you can do something. Okay. Suppose now that an electron can jump into a positive energy level. Okay. So now the distance in energy is twice the mass of the electron, twice mc squared from here to there. So one can create a hole in the electron C by exciting a negative energy electron to a positive energy level. Okay, from here to there. And how can you do that? And it was another huge intuition by Dirac. So suppose that a photon with energy equal to twice the mass of the electron hits the electron here in the highest negative energy level, okay, where the energy is just in minus its mass. Then the electron will take the energy from the photon and can jump here to the first positive or the lowest positive energy level, okay? So what we have here, we have now an electron in a positive energy level and a hole in the first negative energy level, while all the other negative energy levels are completely occupied. So the interpretation is the following. The hole left by the electron in the negative energy level, that corresponds to the absence of a negative charge with negative energy here, can be reinterpreted as the appearance of a positively charged particle with positive energy and the same mass of the electron, that is the positron. So let me repeat this because this is a crucial point. The missing of an electron into these with negative charge into this negative energy level, so this hole here, okay, can be reinterpreted as the presence of a positively charged electron, okay, with positive energy. So something that is physical, positive energy you can of course accept. And this was the idea of the positron. The positron is the antiparticle of the electron. So essentially with this mechanism, Dirac made two fundamental predictions. First of all, the mechanism that you can create a pair of electron-positron with a photon, and essentially the other one is that the existence itself of the positron. That means, in other words, the existence of antimatter. Okay, each matter particle must have a corresponding antimatter particle. And if you make this hypothesis, because at this moment it's only an hypothesis, then you can interpret your negative energy solution, because now they are not anymore negative energy solution, but they are positive energy solution for the antiparticle, the corresponding antiparticle. Okay. So with this new concept of vacuum, Dirac had not only predicted the existence of antiparticle, but also of this photon into gamma pair production, which was discovered, of course, later on. Ok, è chiaro questo concetto, ragazzi?
Le negative sono quelle per l'antimateria.
Sì, diciamo, la presenza di una lacuna nel mare qui, quindi l'energia negativa, viene reinterpretato come la presenza di una particella di antimateria, quindi uguale all'elettrone in tutto e per tutto, tranne per la carica, ma a energia positiva, quindi fisica. Ok?
Ok.
Allora, so this was, of course, an hypothesis at the time. We are still in 1928. But, of course, all these idea had to be confirmed experimentally, okay? So if you are able to experimentally find the positron, that is a huge discovery because this is the discovery of the first antimatter particle, then all this reasoning makes sense and the Dirac theory can survive, okay? So you will also convince the rest of the theoretical community that everything here makes sense. Now, the discovery of the positron occurred just 4 years later, okay, in 1932, and the positron was discovered by Anderson by using a cloud chamber to study cosmic ray showers. You all know what a cloud chamber is and how it works?
I do.
I don't see.
We're not seen it properly during any course or no lectures, but I do know by myself how it does work. Okay, so a cloud chamber is a chamber with some high pressure gas inside in, let's say, metastable state. That means that you just need a small perturbation
to condensate the vapor into bubbles. So suppose now that an electric particle crosses this high pressure gas along the track followed by the particle, very small bubbles will be formed, and then you can make a picture with a photograph of this line of bubbles, and you can therefore visualize the track followed by the particle. Okay? Chiaro? Lo ripeto in italiano se preferite?
No, per me va bene.
Ok, se chiaro per tutti, ok. And the bubble chamber was also immersed in a magnetic field, which is oriented in this way, so with the direction into the slide. Okay. Now, so this was the tool used by Anderson to study cosmic rays, because at the time the only way to do particle physics was study cosmic rays. There were no particle accelerator at that time. Okay, but then during his studies he found some very strange tracks, like the one you see here. Why is this track so strange? First of all, okay, you have a charged particle crossing a magnetic field, so it experiences a Lorentz force like this. That means that the charged particle will be bent, okay, into some kind of circular trajectory by the magnetic field, as you know. So this kind of track here, okay, could be interpreted in two ways, given the magnetic field in this direction. The first way is that of a positive particle coming from the top and moving counterclockwise, so like this, okay? But in principle, you can also have the same track if a negative particle, so given the same magnetic field, of course, if a negative particle, okay, enters from the bottom and move clockwise. Do you agree?
Yes, makes sense.
Okay, so there is essentially a top-down ambiguity, because this track can be explained in two different ways. Either a positive particle coming from the top and bending this way, moving counterclockwise, or by a negative particle coming from the bottom and moving clockwise and bending in this way. So let me just read this. So the curvature and the concavity of the tracks were compatible with either a negative particle coming from the bottom, clockwise. Okay, this is already. Okay, now what was the situation in 1932? In 1932, the only charged particle known were the electron and the proton. Okay, these are the only particles known at that time. So this, for the interpretation by Anderson, this could be either an electron or a proton. Now, of course, electron and proton produce tracks with different features in a cloud chamber, and the thickness and the length of the tracks observed by Anderson, were incompatible with the proton hypothesis. Okay, so overall, everything seemed to indicate the passage of an electron from the bottom to the top. Okay, now, in principle, this can be fine, but this cannot be fine because Anderson was studying cosmic rays, and cosmic rays come from the top, from the atmosphere, not from the Earth, so from the bottom. This thing was put in a balloon in the atmosphere, okay? So it was impossible that the cosmic ray was coming from the bottom, from the Earth through the atmosphere, rather than from the atmosphere to the Earth. And this could not be even a problem. So it was really, so cannot be a positive charged particle. So this was really a problem. Now, in order to solve this up-down ambiguity, Anderson put a layer of lead here in between. And you know that when a charged particle crosses some material, it loses energy into the material, and so of course, we change bending in the magnetic field. Okay, clearly, if a less energetic particle will bend more than a more energetic particle. So in order to solve this ambiguity, Anderson put this lead and made again the observation. And what you see here is that, as you see, the curvature increases in the bottom part. Okay? That means that the particle was coming from the top with higher energy. It lost some energy into the lead. It came out downward with lower energy because it's now bending more here. Okay, so in this way, the top-down ambiguity was solved. Okay, and so we can exclude this hypothesis. Okay, so the particle is indeed coming from the top. but cannot be an electron because the electron is a negative, okay? And so putting all this information together, this was in fact the discovery of the positron, okay? So the track is like the electron track, okay? But it has to have a positive charge in order to be interpreted correctly. So a positively charged electron coming from the top, losing some energy into the lead, and then continue with this higher bending. So it must be a new positive particle with the mass of the electron in order to explain all these observations here. And this observation was in fact constitutes the discovery of the positron, which is the antiparticle of the electron, as predicted by Dirac 4 years later with this C of the Dirac C theory, okay, this theory here, okay. So once we have now an experimental proof of the existence of antimatter, now the whole Dirac theory makes sense, okay, and becomes actually really powerful now to describe relativistic electrons, okay. Now, in 1933, using an improved version of the original cloud chamber, so also allowing for the spatial reconstruction of the tracks, Blackhead and Arcalini not only confirmed the discovery of the positron, but also discovered the E plus E minus production process, which was also predicted by Dirac in the Dirac C theory. Ok? Tutto chiaro?
Sì.
Yes.
Ok, quindi adesso abbiamo una prova sperimentale molto forte a supporto della teoria di Dirac e che dà finalmente anche un'interpretazione alle soluzioni a energia negativa. Quindi quelle soluzioni non solo non vanno rigettate perché fanno parte di un set completo ortogonale, ma possono essere adesso fisicamente interpretate come l'esistenza delle antiparticelle che sono state quindi soltanto qualche anno dopo scoperte. La prima è stato il positrone, poi ovviamente man mano si è andato a scoprire tutte quante le altre particelle e adesso sappiamo che ogni particella di fatto ha una sola antiparticella. Okay, few words about antiparticles. So nowadays it is experimentally established that each fundamental fermion has its corresponding antiparticle, so leptons and also quarks. And antiparticles, they propagate forward in time with positive energy, so they are absolutely physical objects. They have opposite charge compared to the corresponding particle, so the positron has a positive charge, the antiproton has a negative charge, and so on. Just like particles, they ionize the gas in a vacuum detector. Just like particles, they produce electromagnetic shower in calorimeters. And just like particles, they undergo the same interaction. So also antiparticles feel the electromagnetic interaction, the strong interaction in case of quarks, antiquarks, and the weak interactions, okay? However, it is not straightforward to reconcile all these observations, which today are absolutely established, with the negative energy solution that emerged from the mathematics of the theory, essentially. Okay. Now, the reason is the following. Today, the Dirac picture of the vacuum is only of historical interest. Okay. Because these have at least two fundamental conceptual problems. First of all, antiparticle states for bosons, so antibosons, are also observed, okay? But these, of course, bosons do not follow the Pauli exclusion principle, so you cannot reconcile the Dirac theory for bosons, no way. Another problem is that the fully occupied Dirac C implies that the vacuum has an infinite energy, okay? And of course, it is not clear how to interpret this physically, an infinite energy. So Dirac had, let's say, the smart idea of providing an interpretation of the negative energy solution that was further endorsed by experiment, so by the experimental discovery of antiparticle. However, the Dirac picture was essentially not really trustable because it provides at least two fundamental problems. Okay, so what is now today the interpretation? In the modern view, the negative energy solution of the Dirac equation are interpreted in terms of the so-called Feynman-Stackelberg interpretation, which is the following. So the negative energy solution corresponds to, in this interpretation, okay, the negative energy solution corresponds to, indeed, unphysical negative energy particle which propagates backward in time. Backward in time, okay? Now, Since the time dependence of the wave function, okay, is unchanged, if you simultaneously swap e to minus e and t to minus t, here, you get exactly the same. These unphysical negative energy solutions can also be interpreted as physical positive energy antiparticles with opposite charge, now propagating forward in time. So suppose this is the direction of time, which cannot be, which of course is positive. So the negative energy solution of the Dirac equation are interpreted in this Feynman circular interpretation as negatively charged particle moving with negative energy backward in time. But this is reinterpreted as the existence of particles with opposite charge, positive energy, and moving forward in time. So physical particles. Now, of course, we have to reconcile this interpretation with the solution of the Dirac equation. Okay, so following the Feynman-Stackelberg interpretation, the unphysical negative energy particle spinors, U3 and U4, those corresponds to negative energy, can then be written in terms of physical positive energy antiparticle spinors that we will call V1 and V2. And the two can be related in this way, okay, essentially by swapping the sign of both energy and momentum. So the U4, which is a physical negative energy solution, will for a particle, will correspond to a physical positive energy solution for an antiparticle, and also for the U3 with the other solution, V2. Now, this you simply obtain by just swapping E to minus E and P to minus P. But there is, of course, a more formal way to obtain this, and it is indeed to solve again the Dirac equation, but now looking for a solution with the opposite sign in the exponential. So this is the solution that we were looking for before when we solved the question, and which drives to the U1, U2, U3, U4 solution. But now you can also solve the Dirac equation with this kind of solution, so with the antiparticle spinor, V, and with the opposite sign here in momentum and energy. It becomes opposite sign in the exponential part, okay? Which again corresponds to change E to minus C and P to minus P. So this procedure is more formal, but it is equivalent to this correspondence here. U4 with V1 and U3 with V2. So what we have now, we can now solve again the Dirac equation with this kind of solution, and we will obtain a new set of 4 solutions now for antiparticles. So the V1, V2, V3, and V4, just following the same step. And again, the V1 and V2 will be positive energy solution, and V3 and V4 will be now negative energy solution. So let's put now everything together. In total, we have now 8 different solutions for the Dirac equation, U1, U2, U3, U4, and V1, V2, V3, V4. Although, of course, only 4 are independent, okay? So the U1, U2, V1, V2 are the positive energy solution, and the U3, U4, V3, V4 are the negative energy solution. These are in total 8 solutions. We have to choose 4 of them, because only 4 are independent. And although one can make any choice of those, okay, clearly it is more natural to work with the 4 positive energy solutions, okay, corresponding to physical particles and antiparticles. So from now on, we will not anymore consider these 2 set of negative energy solution. We will only work with positive energy solution, that means physical solution, 2 of which are for particles, 2 of which are for antiparticles. Okay, so U1, U2, V1, V2. And this is what we'll be using when we'll be calculating a cross-section through the Feynman diagrams that we will see in the next lessons. Okay. Now, having understood the meaning of positive and negative energy solution, we still have to understand why there are 2 positive and 2 negative solutions. So what is now the interpretation of this twofold degeneracy here? Okay, and this we will see next time, ok? Next Wednesday. Quindi oggi ci fermiamo qui, continueremo poi mercoledì prossimo e cercherò anche di spiegare appunto perché in realtà abbiamo questa degenerazione doppia, perché ne abbiamo 2 soluzioni per ciascuna di queste. Ok, domande, dubbi?
No, io sono a posto.
Ok.
Prof?
Sì.
Io non ho esattamente capito la differenza tra l'interpretazione di Dirac delle soluzioni negative e la soluzione moderna. Nel senso, c'è un passaggio che mi sembra identico, quindi non ho capito.
Allora, lui, diciamo, Dirac diceva che quelle negative non vanno rigettate perché sono interpretate come antiparticelle positive. Sì, diciamo, questa parte qui è comune.
Ok,
Perché anche nella diciamo, nell'interpretazione di Feynman Stuckelberg fa esattamente la stessa discussione. Aspetta che la riprendo.
in pratica quella moderna esclude l'idea del mare.
Escludere il male perché diciamo, quello porta a dei problemi concettuali grossi, perché non si può applicare ai bosoni, mentre sappiamo che anche i bosoni hanno antiparticelle, e poi perché un vuoto con infiniti livelli di energia completamente occupati ti porta a una energia infinita che chiaramente non è fisica. Diciamo, il passo avanti che è stato fatto con Feynman-Stuckelberg è anche quello di indicare la direzione del tempo, ok?
Ok.
Quindi le situazioni negative, l'energia negativa, insomma, vanno in effetti diciamo, reinterpretate perché in questa interpretazione corrispondono a oggetti che si muovono indietro nel tempo, che chiaramente non ha senso, ok? E quindi tu cosa fai? Inverti il senso del tempo, da negativo diventa positivo, inverti l'energia e per conservare la carica deve anche invertire la carica, perché una mancanza di carica positiva da questo lato corrisponde, una carica negativa da questo lato corrisponde a una carica positiva dall'altro lato. Quindi questa è l'interpretazione, ok?
Va bene.
Ok. Quindi vabbè, siamo arrivati qui, adesso diciamo da ora in poi, come ho già detto prima, non ci cureremo più di queste 4 soluzioni qui, ma il set di 4 soluzioni ortogonali delle possiamo dire che useremo saranno queste qui, ok? Tutte fisiche, tutte energia positiva, di cui diciamo 2 riguardano le particelle e 2 riguardano le antiparticelle. Ok, ci sono altre domande, posso chiudere, interrompere la registrazione e ci vediamo noi mercoledì alle 9.
Arrivederci professore, buon weekend.
Arrivederci, buon weekend anche voi.